All right, so here's the 2022. This is set 1 of the mechanics set. So lately, the last couple of years, they've been doing 2 sets. So this is set 1, and then there's going to be set 2 is in a different video. But these are the AP Physics C mechanics set 1 free response questions from 2022. If I have any mistakes, I'll put them in the pinned comment below, and you guys can see that. All right, so block M, mass M is pulled across a horizontal table by a string connected to a motor as attached to the floor. The string passes over a pulley with negligible friction that is vertically aligned with the left edge of the table as shown. The string and pulley both have negligible mass. The pulley is a height h above the table. The motor exerts a constant force tension Ft on the string, and the block remains in contact with the table at times as the block slides across the table from L to 0. The coefficient of kinetic friction between the table and the block is mu k. Express all your answers in terms of these variables they gave you. All right. On the dot below, draw and label forces that act on the block when the block is at x equals L. Each force must be represented by a distinct arrow pointing away from the dot. Okay, so free body diagram of this guy. We got gravity going down on the block. We have a normal force from the table. What else is touching it? Right? The rope is touching it this way like that. Nothing else is... we got friction, right? So then we got force of friction here because there's table. There's nothing else touching the block. So those are the forces you got to include. mg, normal force, frictional force, and then tension force. Call it Ft. Because they called it Ft, so we'll just call it. All right. Derive an expression for the angle theta makes with the horizontal as a function of x. So as a function of x, we have to figure out what is the angle theta that it makes here. I think this is a geometry question, right? Like basically... let's say he's located at x here. Like this variable here is x. And then this is a right triangle. This is h. So what's the relationship between theta and x and this height h is a right triangle? You just say tangent of theta is h over x. So tan theta equals h over x. Oh, sorry, capital H. And so therefore x is equal to h over tan theta. Okay, I think that's all you do. It's just a geometry question. I don't think there's anything to do at that point. So we're probably going to use that. Derive an expression for the normal force exerted on the block by the table as a function of the block's position x. So we needed this... I'm sorry, what I'm doing. I need to solve for theta, not solve for x. So derive an expression for the angle theta. So theta is tangent inverse of h over x. Okay. So derive an expression for the normal force exerted. So what we always do at this point is I'm going to take a picture of this, put it in here so you can kind of see what we're always going to do is we're always going to break things down into the horizontal vertical components and do net force equals MA, right? So we're going to do, we'll just do the vertical forces because this deals with the vertical forces. Well, I'll do the both. I might as well do both at the same time. F net equals MA. We'll do the horizontal direction. Let's say it's accelerating to the left there. So we would say, we got to decompose Ft into their constituent components, right? This is Ft cosine theta. This is Ft sine theta because this angle here is theta. So then we're going to say, x direction, we're going to say Ft cosine theta minus force of friction equals ma. And in the y direction, and it is accelerating probably to the left. And in the y direction, we're going to say Fn. So Fn is the positive direction. Let's say this up is positive, left is positive. Then we're saying Fn is positive, Ft sine theta is also positive. And then mg is negative, it's downward. So Fn would equal mg minus Ft sine theta. Okay, so now we want to we can't put our answers in terms of theta because I'm always keeping in mind what are the variables I'm allowed to put everything in terms of. So I have to look at sine of theta, and I can do it in terms of x, which is fine. So if I look at my original triangle, sine of theta is going to be adjacent over hypotenuse. This hypotenuse is square root of x squared plus h squared. So sine would be opposite over hypotenuse. It would be h over square root of x squared plus h squared, like that. And so that's what I would use for sine of theta. So this is going to mg minus ft times h over root h squared plus x squared. And I'm allowed to use all of those variables, I'm pretty sure. I can use m, let me just double check. I can use m, I can use g, I can use ft, I can use x, yeah, and that's fine. And I can use L technically if I wanted to. Okay, awesome. So derive an expression for the magnitude of the net horizontal force exerted on the block as a function of position x. Oh yeah, when they said in function of x, they definitely wanted x in there. So I have this x. How about the horizontal net force? So now we're going to look at this guy, net force horizontal. That is Ft cosine theta minus force of friction is the net force horizontally, right? Because it was this force and this force. This is Ft cosine theta minus mu Fn. I'm sorry I have to keep scrolling back up to the, it's mu k Fn. Luckily, we know what Fn is, so we can plug that in for Fn. What is Ft? Ft is fine, but cosine of theta, let's just redraw the triangle here for our reference. So this is theta. This side was x. This was h. This was square root of x squared plus h squared. Oops. So what we have here is the cosine of theta is adjacent over hypotenuse. So cosine of theta would be x over root x squared plus h squared, right? So then this is going to be Ft x over root x squared plus h squared minus mu k times this whole normal force thing, mg minus ft h over root x squared plus h squared. Right, and I'm just going to leave that like that. I'm not going to simplify any more than that. You could probably like group the mu k's and factor out. I don't know. It's just not worth it. I'm just going to leave it like that. Derive an expression from magnitude. Yeah, okay, yep. Okay, write but do not solve an integral expression that we use to solve for the work done by the string on the block as the box moves from L to... okay, so the integral is going to be f dx, but remember we have to do the force that is parallel to it, and it's the work done by the string. So I care about the tension that's in the direction of the displacement, right? So that's t, that's the ft, this is going to be the integral of ft cosine theta dx. But remember that we want the cosine theta in terms of x because I'm integrating, because theta is a variable that changes, right? And so then you would say that's the integral of this thing here. Work done by the string. So that's ft times that. ft and then x. What did I say? Cosine is x over root x squared plus h squared, right? And now I want to integrate it from 0 to L. And that's fine. I think they said the tension was constant, right? Constant force tension. So I don't have to do anything with the tension force because it's constant. It's not changing as a function of x. So I would do this integral right here. Okay. Does the string do more or less for the same amount of work on the block as the block moves from L to L over 2 compared to when the block moves from L over 2 to x equals 0? So really you want to compare whether or not, so if you think about what's happening, I know I'm scrolling back up. If you think about the original problem, what's happening here is in this part here, right, the tension is the same, but the component parallel to the tension is less, right? And the tension is constant. So as he gets closer, right, what's happening is the tension force is becoming more vertical. That means there is a smaller component parallel to the displacement, right? And that makes it so that it's doing less work because it's moving over the same distance, but it's the FT component parallel to that that ground is less. So we would say it does more work when it moves from L over L2, and I would say FT cosine theta has a larger component or larger value when x equals L to L over 2, and thus over the same displacement. Thus, the work is greater. It does more work. And you can write the equation if you want, integral ft cosine theta dx or something like that. You could just say like the work is equal to that. Okay, awesome. So that was the first one. All right, let's look at the next one. Cart 1 of mass m1 is held at rest above the bottom of the incline. Cart 2 is a mass of m2, where m2 is greater than m1 is at the rest of the bottom of the incline. Time t equals 0. Cart is released, travels down the incline, and smoothly transitions to the horizontal section. The center of mass of cart 1 moves a vertical distance h as shown. At time tc, cart 1 reaches the bottom of the incline and immediately collides sticks to cart 2, so it sticks. After the collision, the two-cart system moves with speed v. Frictional rotational effects are negligible. During the collision, is the impulse on cart 1 from cart 2 greater than, less than, or equal to equal magnitude of the impulse of cart 2 from cart 1? They are equal. Newton's third law of motion. Newton's third law. Impulse equals the force over the time. The collision is the same amount of time. It's the same time on both carts. But the forces are equal and opposite. Equal and opposite. So what does that mean? That therefore Ft is equal and opposite. Okay. So that's just Newton's third law. If m1 hits m2, m2 pushes on m1 with the same force. On the following axis, draw the graphs of the magnitude of the momentum of each cart as a function of time before and after the collision. The collision occurs in a negligible amount of time. The grid lines and graph are drawn to each scale. So we probably need to calculate some things here. We would say, m2 is bigger than m1, so we have relative values. But if I were just to do an analysis of this, it would be m1 gains some momentum as its velocity is moving at a constant speed, so it's gaining momentum here. And then so before, up until the collision, m1 is moving upward as it's gaining a fixed amount of velocity here. And this guy is starting at 0. So before the collision, right, cart 2 is just sitting there and cart 1 is accelerating. Then after, M1 has to lose some momentum, right? Like it has to lose momentum. We'll say it loses some momentum. And then, but this guy has to gain the same amount of momentum. Now, because the masses are different, they're going to have the same momentum. Well, no, they're not going to have the same momentum afterwards. They're going to have the same speed afterwards. So maybe what I should do is I should sketch it like this. I should sketch it like here, then here. Then this guy loses more momentum and this guy gains. Because ultimately what's going to happen afterwards is this guy has to gain momentum, and the total momentum should equal the original momentum, right? As well as mass of cart 2 by having more mass but the same speed as cart 1 after the collision ought to have more momentum. So you probably want a couple things to note here. The one, that's a straight line, and that cart 1 loses more momentum, cart 2 gains the same more momentum, and that the total momentum equals this. So like these 2 plus this 1 gives me this 3 here. And that would be sufficient. Now, to emphasize, why is there a difference here? M2 is greater than M1, but they're moving at the same speed, right? So therefore, M2V is greater than M1V, right? Now, I don't know, it's twice as much. That part you don't have to be specific. It doesn't be twice as much. Just that this one is greater than this one, and that the total equals the original momentum before the collision. All right, show that the velocity of the two-cart system after the collision is given by this equation. So when he's going down the cart here, so first M1 has to gain kinetic energy as he's falling that distance h. So the first thing I want to figure out is how fast is cart 1 moving before he collides. Well, here you could just do m1gh equals 1/2 m1v squared, or v1 squared, and the m1's cancel, and you can find v1 is square root of 2gh. Okay, that's step 1, to find the energy. So that's what v1 is right here. And then afterwards, so this guy's not moving, this is m2, Now we do conservation of momentum. So before the collision, the momentum is m1 times v1, which is m1 root 2gh. After the collision, they move together at a velocity v, and you're just going to set these equal to each other. And then you could solve for the v. V is m1 root 2gh, and just divide by this m1 plus m2. Okay, and then 2g, yeah, okay. They just wrote it weird, but this is the same thing. Root 2g, root h, and then m1 over m2. Okay. A group of students use a setup to perform an experiment. They measure the mass of cart 1 to be 0.25 kilograms. The mass of cart 2 is unknown. The students perform several trials. At each trial, cart 1 is released from different heights, and the final velocity of the two-cart system is measured. The students' graph function of root h is shown. Draw a line that represents line of best fit. You guys should have rulers or things like that. But you know, I'm just gonna pick something like that. You guys should have rulers, something better than what I'm using. I just free-handed that, which isn't great. Use the best fit line to calculate the mass of cart 2. Okay, so what do we have here? Well, we look at our equation, right? So our v was equal to m1 over m1 plus m2. If you couldn't derive it, right, they gave you the equation. It's root 2g root h, right? So like if you say this is my y value and this is my x variable, right? That's my x and y axis. Then the slope tells me this thing right here. This is my slope right here. So if I'm going to estimate a slope, I'm going to pick 2 points on the curve. Let's just pick, I don't know, we'll just pick this point here, and I didn't make it. Okay, so I'm going to pick a little bit better of a line. I'm going to try to draw a better line here. I will use a line so I can attempt to, and then maybe move this down a little bit. I know I get to adjust it, but it's really hard without a ruler to sort of do that. Okay, cool. So then we're going to pick 2 points. We'll pick, say, this point right here. And then we'll pick, I like to pick 2 points that are far away. It'll just be more accurate if you do that. So what is that? That's like this is 0.3. We'll call that 0.35. We'll call this 0.6 on the y. And then we'll call this 0.85. No, not 0.85, 0.95. 0.9 is halfway between here. So 0.95, and then we'll call that 1.6. So the slope is going to equal 1.6 minus 0.6 divided by 0.95 minus 0.35. That's 1 over 0.6. 1 divided by 0.6 is equal to 1.67. Okay? Now, that's equal to this thing. So we have m1 over m1 plus m2 root 2g equals 1.67. And we can use m1, let's say it's 0.25 over 0.25 plus m2 square root of 2 times 9.8 equals 1.67. Okay, so I'm just going to multiply this guy to the top, move that to the bottom. So 0.25 root 2 times 9.8 divided by 1.67 would be 0.25 plus m2. And then I can solve for m2 by just subtracting 0.25 from there. And I get 0.41 kilograms. Okay. After the experiment, the students used the balance to measure the mass of cart 2 and find it to be less than what was determined in part D. To explain this discrepancy, one student proposes that the mass of cart 1 was incorrectly measured in the beginning of the experiment. The student measured mass of cart 1 again and recorded a new value m1 prime. Should the student suspect that m1 prime will be greater than, less than, or equal to 2.25 kilogram? Okay, so this is kind of an interesting. So if I look at, maybe one way to do this is to look at your expression here. Look at what m2 is. M2 is, in terms of m1, like you could have solved it in terms of m1. And what I would have said is m2, like all the 0.25s are just m1. So I would have done m1 root 2 times 9.8, 2g over 1.67. That's our data, right? Minus m1. I think that's what I got there. That's what I ultimately derived here. So what they're saying is this side was smaller, So what would I expect M1 to do is this number here, by the way, if you look at this one, this is a number I can calculate. What is root 2 times 9.8 divided by 1.67 there? This is 2.656 M1 minus M1, which is 1.656 M1. So ultimately, if M2 goes down, M1 should have gone down either. So the solution would be if M2 it's less than what we determined, that means M1 is probably smaller. So I would expect this one, and this justification is fine. So as M1 decreases, M2 should have decreased as well. Okay, that's the dependency that I'm talking about there. Okay, cool. All right, number 3, we got a solid uniform disc supported by a vertical stand. The disc is able to rotate with negligible friction by axle passes through the center of the disc. The mass and radius of the disc are given by M, D, and R respectively. The rotational inertia is given by this. A string of negligible mass is draped over, negligible mass draped over the disc attached to the top of the disc at point P. One end of the string is connected to an unstretched ideal spring of spring constant K, which is fixed to the ground as shown in figure 1. Okay. The block mass MB is attached to the spring on the right side. Let's see. Sorry, someone was calling. The disc is rotated clockwise through a small angle theta. Give an algebraic expression in terms of for physical constants as appropriate. Derive an expression for the mass MB of the block. And what I have is I have the mass of the disc, I have the radius of the disc, I have the spring constant K, and I know the theta of how much it rotated by. Okay, and they want to know, okay, so what you have to understand is we need to know how much the spring was stretched, because ultimately, if you look at the whole system, once this guy is suspended, right, like if I draw a free body diagram of the block, right, I would say mg of the block equals the tension of the force, because it's suspended there, right? It reaches equilibrium, so it's just sitting at that point. And this tension is uniform here, and we have tension here, and then a spring force on this guy. So the spring force has to equal the tension ultimately, right? So I would say the spring force has to equal the tension, which is equal to mb times g. Okay, because those are the only forces acting. Now, the spring force is kx equals mbg. Now, I'm not told how much the spring was stretched by. I'm told how much the angle was swept by. But if this thing rotated a certain amount, right, what is the distance that it rotated? The distance that it rotated by an angle theta is, you say that distance is r theta. That's from your pre-calculus days. So the x is r theta in this instance. That's how much it's stretched by. So the x I can replace with r times theta. So the mb is equal to k r theta over g. Like that. Now the theta here does need to be measured in radians when you're doing that, technically. Okay, so just keep that in mind. But that is that would be the correct relationship between how much it rotated in that linear kind of motion at the end, or like how much distance the spring was stretched. Okay, at time t equals 0, the string on the right side of the disc is cut and the block falls to the ground. On the circle below, which represents the disc, draw and label the forces, not components, that act on the disc immediately after the string is cut and the block is falling to the ground. Each force should be represented by the arrow that starts on directly away from the point of application. So if I look at this guy, I've now cut the string, so I only have tension on. So what's touching this thing? Well, I definitely have gravity. Okay, I definitely have a tension force here, and I definitely have some axial force here. You could call it a normal force. I usually call it an axial force. I don't know if they're super picky about that. So this is mg. This is a force from the axle. And then there's tension here. Now, I'll just call it ft. I know I like to use t, but we'll just call it ft. They prefer that you put ft. I don't know. Maybe it's confusing with period. Okay, so that's everything. The last thing I asked myself, is there anything else touching it? Well, there's a rope here, but it's slack at this point, or like a little bit slack. Actually, yeah, negligible mass. Yeah, I think at the moment there's a tension right there, but like technically it might disappear shortly. But okay, so determine an expression for the angular acceleration of the disk immediately after the string is cut. Okay, so the only, like, if this is the axis of rotation here, right? Neither the axle nor the mg apply any torque. The only torque is from ft here, right? So we have ft equals, the net torque. So what are we going to do is we're going to do net torque equals I alpha. That's how we're going to get the angular acceleration, right? So the net torque is just ft times r equals I times, they gave us I. I'm pretty sure they gave us I. I was 1/2 md r squared. 1/2 md r squared times alpha. So simplifying, one of these r's is going to cancel. Oh, and I need to find what ft is. Well, we've just cut the string, so the spring is still stretched, right? So it's still equal to kx or kr theta, I think. So we'll do kr theta equals 1/2 md r alpha, and then now this r cancels with this thing. And so the alpha is equal to 2k theta over md. Yeah, that would be it. Did I do everything right? Kr theta is the spring force, kr theta, so the r squareds will cancel. So, okay, I think I did that right. I don't see any obvious mistakes now I'm looking it over. If I were really taking the test, I would probably double check that a little bit more. But what variables am I allowed to use? MD, RK, theta. MD, RK, theta. Yeah, I have the right variables. Okay. At t equals t1, the disk is rotated and point P is again directly above the axle. Sketch a graph of the magnitude of the angular velocity of the disk as a function of time from t equals 0 to t1. So I was going to think about this. There's an angular acceleration, but it's gonna loosen as the spring relaxes, right? So the torque's going to reduce as it relaxes. So that means the angular acceleration should reduce. So that means it's going to have a positive angular. So it starts from rest, but the slope should be big, and then it should it's back at point P. Once it's back at point P, I think the spring is totally relaxed, unstretched. So you should have a zero angular acceleration at that point. So that means I should have a slope that's 0 at that point. So it should start, just to be clear, because the slope is the angular acceleration, it should start with a steeper slope, but it will just kind of decrease and go flatten out to 0. Now, if I were more rigorous, I should probably derive an expression that relates the two to make sure. But I'm pretty sure it's going to have to end with 0. It's going to have to start with it, and it's going to have to gradually decrease. So it's concave down and things like that. They did not say anything about labeling things, so I'm not going to label any values or computations on there. So I'm just going to have that general shape there. The disk is adjusted so that on the support, so the axle does not pass through the center of the disk. The block is again hung on the right side, and the spring disk block system comes to equilibrium, as shown in Figure 3. The axle does not exert a torque on the disk. I don't know why they told you that, but that is true. The axle is not going to exert a torque on it, I guess. Well, okay. It could, I guess, theoretically. For each force on the disk, indicate whether the magnitude of the torque about the axle is caused by for each force on the disk. So then when you do the free body diagram of the disk, indicate whether the magnitude of the torque about the axle is caused by that force increases, decreases, or stays the same relative to part B. So we do a free body diagram of this guy. We're going to talk about, this is tension. Part B. Part B was the one where we cut it, right? So is it that we cut it again? Okay, so imagine we cut it again, I guess. So there's no on this guy. So we've got gravity here. And we have the axial force here. Right? Those are the three forces from part, part A, kind of the free body, or part B. Yeah, we had the free body diagram. FT, MG, and F axle. So let's talk about each one. Well, they said the axle doesn't exert a torque. Okay, so the F axle, and this is the axis of rotation, by the way, if you're going to do that. So the F axle is no change. It acts at axis of rotation. They didn't tell you what the axis of rotation, but it's spinning around here. So X at the axis of rotation. Yeah, axis rotation, so no torque. Okay, and then mg, it now has more torque, so it increases because it no longer acting at axis of rotation and perpendicular to the r vector. Right? Because this now has a torque, because if you draw an arrow from there to there, it now has a torque. This one, the torque reduces because the r reduced, right? Ft reduces, Ft decreases because the r decreases. Or you could put in parentheses, say the Ft is applied closer to the axis of rotation. And I might want to just make a specific note. All forces, so mg and Ft have the same magnitude. So all we're really focusing on is really about their r value, how the r is relative to the axis of rotation. So mg increases because it was 0, and it was 0 before. Maybe I'll just add that in there. And Ft decreases like that. Okay, cool. That was it.